So good morning, all of you. A very good morning, all of you. Okay. Just I'm starting this session. Okay. Who are actually sitting near to the TV, please, near to the television, please come outside of that room so that it is perfectly audible for you. Okay, good morning, all of you. In the studies class, in the studies session, we have discussed about the power angle curve. That is, we will draw that curve when we are discussing about the transient stability, which is an important one. So we have derived one equation, that is the three important equation, that is VSVR by X, which is a maximum power, VSVR by X sine delta, which is the synchronous power, VSVR by X cos delta, which is a synchronous power coefficient. Okay. Anyway, this is actually a maximum power which we are going to use, and this is actually the VSVR by X sine delta, which we are going to use this one, so that we are going to draw the curve between power. So now let us discuss about, and we have also derived one condition where the transfer reactance should be equal to √3 times of a resistance and resistance. So maximum power can be get transferred. Okay, whatever you have seen the formula, that is EV by X sine delta, that is the power delivered or power transferred. So now let us determine the steady state stability. How we are going to discuss about the steady state stability. As we already know, the steady state stability is an ability of a power system to restore its initial conditions. That is, it will commit to maintain the synchronism even after a small and gradual disturbance. So we are going to call it as a steady state stability. Yesterday also we have discussed about these definitions. Okay. So we have different types of stabilities. We have different types of disturbances. So to determine the steady state stability, let us take one example. So just I'm considering one example. So consider one synchronous generator, consider one transmission line, consider also one infinite bus. Okay. What is actually infinite bus? Infinite bus is nothing but where the voltage and frequency will remain constant forever. We are going to call that as an infinite bus. So synchronous generator will have the V1 or a Vs, which we already know, at an angle of delta, and transfer reactance as X, and the infinite bus will have a terminal voltage of V2 at an angle of 0 degrees. So now, this is under the, for example, under the stable operating condition. Stable operating condition means it is going to deliver some amount of power. The transmission line are going to receive that power, and it will transmit from the generator side to the load side. Okay. So the load is a constant. Now the transmission of power is a constant. the generator, what it is delivering is a constant. So there is no disturbance. That is, there is no fault or there is no change in the load or there is no disturbance up to one condition. So we are going to call that as an initial condition. Initial condition means where the amount of power delivered is a P naught, and at that time the angle is called as a delta naught. We are going to call that as an initial condition. Initial condition means before disturbance condition. Okay. So now suddenly what happens? Suddenly we are going to take one example that load is changed. Load inside, the load is increased. So when the load is increased, then we are going to give the termination as delta P. Delta P is nothing but an change in load. Okay, change in active power. How much the active power is changed at the at the load inside, we are going to call it as a delta P. Okay. So which we are going to find out how the machine is going to behave as a stability. That is how there will be change in the active power with respect to change in the delta at the synchronous machine. If you want to observe means, because there is a change in power at the load end side. So if there is a change in the power at the load end side, there should be also change in the power at the generator end side. Are you understanding the point? There is no way related to the transmission line. Transmission line will not do anything. Whatever the power it is receiving from the generator, it will transfer to the load. That is actually the duty of a transmission line. It will not generate or it will not change anything. So whatever the load have been changed here, the amount of power have been changed at the load end side, it will be also reflected at the generator inside. Right. So based on what condition we are going to use to find out that one, we are going to use one equation. We are going to call that as a swing equation. Are all of you listening? Shall I continue?
Yes, sir.
So for that reason, for better understanding purpose, what am I doing is just what actually the swing equation. Swing equation is nothing but, and this is the equation which we are going to derive under the transition stability condition. But this is actually a swing equation. We are going to call this as a swing equation. Okay. M d square delta by dt square is equal to Pi minus P. Okay. M we are going to call it as moment of inertia. That is inertia of a rotor. Of a synchronous generator, we are going to call it as M. D square delta by dt square is the equation, that is how much the angle is going to change with respect to time, and Pi is the input power of a synchronous generator, nothing but a mechanical power or shaft power. PE, this is not P naught, this is a PE. PE is nothing but an electrical output power of a generator. So just I will take one example. You can see here. So this is actually a synchronous generator. Okay. So synchronous generator which it is connected to one bus. So whatever the power we are getting, that is whatever the power the generator is receiving, we are going to call that power as shaft power or mechanical power or input power. Whatever the generator is giving or delivering, we are going to call that as electrical power. Okay. So what is this delta? You can write, we are going to always name it as a delta. Okay, E at an angle of delta. What is this delta means? So if you have access, if you have a knowledge of synchronous machines, I think you know this is a stator axis. No, this is actually a stator axis. This is the stator axis. This is a rotor axis. This is a stator axis and this is a rotor axis. Okay, so this is the stator axis and this is the rotor axis. And the angle difference between the stator axis and rotor axis is nothing but delta. Okay, the angle difference between the stator axis and the rotor axis is nothing but a delta, and this stator axis is a fixed axis. It is not going to move. This is nothing but an angle difference between the stator magnetic field and the rotor magnetic field. Here also the angle difference between stator axis and the rotor axis. So this is nothing but a fixed. So whenever it is fixed, Now what happens, it is going to run with one condition. That one condition is, we are going to call this as accelerating power. EA is equal to shaft power minus electrical output power. Okay, this is nothing but a condition as accelerating power. We are going to call it as an accelerating power. Accelerating power is equal to shaft power minus electrical output power. So if you neglect the losses, whatever it is available under perfect steady state or equilibrium condition, this will be equal to 0. So that means if you are running one synchronous machine, synchronous generator, this electrical power will be get delivered based on the shaft power. So what is this electrical power? Electrical power will also depend on the load what you are connecting here. Okay, depending on the load only, it is going to generate the electrical output power. Please understand this important point. Depending on the load what you are connecting, this electrical power will depends on this load power value, and this electrical power is going to depend on the shaft power value. Because if you want to change this electrical power, what you need to change? You need to change the shaft power. Without changing the shaft power, it is not possible to change the electrical output power. Without changing this electrical output power, it is not going to change this load power. Okay, that is the main logic behind the synchronous machine. That means, see here, so the shaft power is equal to electrical power. That means it is equal to 0. That means it is going to run under this condition, that is stator axis and rotor axis with a delta with some excitation voltage as E. So that means we are going to call it as, it is neither accelerated nor decelerated. It is running under perfectly stable condition. Okay, there is no disturbance. So up to now there is no disturbance. Now what we are doing, this is under no disturbance condition. Now what we are doing, we are changing the load. The load is increased. Now the load is increased. Where the load is increased? At the load end side. So at the load end side, the load is increased. So when the load is increased, what happens to this PE? The load end side, the load is increased. So when the load is increased, the electrical power output power should also increase. Is this right? Is this right? That is, electrical output power should also increase to satisfy this load. So that means what happens? This electrical power, output power is now increasing. So whenever this electrical output power is increasing, so what is this one? This one will give you a negative value. Why it is giving you a negative value? Because this output power should need to vary, but whereas the shaft power will remain as a constant. It is completely a constant because the load is changing within a fraction of time. The electrical power is also going to change within a fraction of time, but the shaft power will not change within a fraction of time. It is not that much easy to change the shaft power. Therefore, the shaft power is a constant, but the electrical output power is increasing. Why it is increasing? Because there is an increase in load. Just because of that reason, there is increasing. You can see here, if you see here, there is Pi is an input or shaft power, which is remain as a constant, but here there is a change. P naught, PE or P naught, you can consider as an output power plus delta P. Delta P is change in the load power. Okay, only this term is changing. So whenever this term is changing, what happens? You will get a negative value. Why you are getting negative value? Because this is a constant. Anyway, the shaft power is a constant, but the electrical power is increasing. Therefore, you will get it as a negative value. That indicates that it is, if it, just because of a negative value, it will start deceleration. It will start deceleration means this rotor axis is going to move towards the stator axis when it is under the deceleration condition, and there is change in the delta. So there is change in the delta. Whenever I'm saying that if there is any disturbance, the delta is going to change. How the delta is going to change? The delta is going to change based on this accelerating power equation. Based on this accelerating power equation, and therefore either it is accelerating or decelerating, then there will be change in this rotor axis. Okay, so whenever there is a change in the rotor axis, this delta value will also change, and we are going to call this change in rotor axis. This change in rotor axis is called as a swing. We are going to use the terminology as a swing. Swing is when there is a change in the rotor axis. When the rotor axis will change, when there is a disturbance, either the disturbance is due to the load, either the disturbance is due to the transmission line, there is transmission line faults, or either the disturbance is due to any condition. Any disturbance will change the rotor axis, therefore it will change the value of delta, and we are going to call that as a swing, and we are going to derive that equation with respect to this one, that is called as a swing equation. So you can see here it as a swing equation. Okay. So we'll derive the swing equation later when we are discussing about the transient stability. Now coming to this part, what happens here? Now we are increasing the load. Just because of increase in load, there will be a negative. That negative is nothing but a change. This one we are going to write it as this change in active power. We are going to write it as dp by d delta. Okay, this is a condition where under the initial, that is when there is no disturbance, into how much angle it is changed, delta delta. I've already told now that angle is going to change when it is getting decelerated. So that change in angle we are going to write down here. And this dp by d delta is when under the initial condition, whenever there is no disturbance. So this is md squared by delta by dt square is equal to minus dp by dou p by dou delta at delta is equal to delta naught into change in delta delta. So now just we are rewriting this d by dt as p, therefore you will get mp square. P is nothing but d by dt. If you derive this one, so you are going to, this is actually a characteristic equation. For this characteristic equation, you are going to find out the two roots. So these are actually the two roots. Plus or minus dou p by dou delta when delta is equal to delta naught divided by m. So these are the two roots. Okay. So these are the two roots. So that means one roots where the roots are pure and imaginary, and where the roots are one positive and one negative, that is real. So we have two different types of roots. So with respect to that one, we can able to divide the dp by d delta, that is change in active power with respect to change in load angle. That is, whenever there is a change in the load angle, how much power is changing at the synchronous generator is called as dp by d delta. Either the change is a positive, or either the change is a negative, or either the change is a zero. So we have three conditions. Either the change may be a positive, either the change may be a negative, either the change may be a zero. Depending on these three conditions itself, we can able to say that either the stability is achieved or not. Either the system is steady state stable or not. We are going to decide based on these three conditions itself. Okay. That is, so when dou p by dou delta is equal to positive, when delta is less than 90 degrees. So dou p by dou delta is equal to negative when delta is greater than 90 degrees. It is equal to zero when delta is exactly equal to 90 degrees. So we are going to call the first one as a stable system, second one as an unstable system, third one as a critically stable system. Okay. So these are the three conditions. So why we are finding this one? We are determining the steady state stability. That is, we are determining the condition where the system is going to achieve stable or not. So when it is going to achieve the stable, it is going to achieve the stable when dou p by dou delta is a positive. That is, when the delta is less than 90 degrees itself, dou p by dou delta is equal to negative. That is unstable when the delta is greater than 90 degrees. So when the change in active power with respect to change in delta, that is dou p by dou delta is exactly zero. That is when delta is equal to exactly 90 degrees, critically stable system. So these are the three types of steady state stability conditions. So based on this one itself, we are going to determine either the system is stable or not. So as we already know, for example, if I want to draw the characteristics, I can able to draw the characteristics like this. I will show you. So if I want to draw the characteristics, you can see. Okay, this is actually a power transfer equation based on the power transfer equation. So what happens? So this is actually, I have already told now, because P is directly proportional to sine delta. P is directly proportional to sine delta because P is equal to EV by X sine delta. If you are assuming EV is directly proportional to sin theta. For that reason, I have drawn this sinusoidal curve. You can see this is actually a maximum power. That is when delta is equal to 90 degrees. So when delta is equal to 90 degrees, this is actually a maximum power which the synchronous generator can able to deliver. This is called as a maximum power. Okay, by this equation you can see in this equation we have that one. See, this is actually a maximum power. Okay? VSVR by X when delta is equal to 90 degrees. When delta is equal to 90 degrees, what happens? You will get this as a maximum power. So that value is this. That value is this one. So now what we have determined, now when we are determining this condition, we have done that at less than 90 degrees, whatever the disturbance we have, whatever your we have a disturbance, either the load disturbance or a transmission line switching disturbance or a generator, any disturbance, if whatever the power is under this condition only, if it is under this condition only, then we are going to call it as a stable condition. It is working under the steady state stable condition because it is under the less than 90 degrees. If it is crossing this junction, if it is beyond the 90 degrees, then we are going to call the synchronous machine is losing the stability. That is, it is losing the synchronism. Okay, it is nowhere it is going to achieve its stability. For that reason, you need to make the synchronous generator out of the system to protect the power system network, because it crosses the 90 degrees, because it is greater than 90 degrees, it crosses the 90 degrees, which it is going to operate under unstable condition, which it is. So if it is exactly at this point, we are going to call this as a critically stable condition, which it is nothing but not a practical, it is just a theoretical point of view, because practically you may be able to see stable, unstable, or it's sometimes under the theoretical you're going to see also this critically stable, where it could be able to deliver the maximum power. Okay, so this is actually a determination of a steady state stability limit. So what we have done, what we have gone through, this one is steady state stability means we are trying to achieve one condition. What is that condition? That condition is how the active power is changing with respect to the change in the delta. So when the delta is changing, how the active power is changing, we have gone through, and we have done one condition so that if it is less than 90 degrees, if it is greater than 90 degrees, it is equal to 90 degrees. Okay, therefore we can able to achieve the steady state stability if it is less than 90 degrees. Okay, that is the thing what you have done. That is called as a determination of steady state stability. Okay, that is not a determination of steady state stability. So we have done this one. So now, for example, we can also derive one condition which we have already done, but including the action of dp by d delta. So for the systems to be stable under the operating condition, what we are going to do, we are saying that dp by d delta is a positive. Okay, dp by d delta is a positive. So that means it is a greater than 0. If it is a negative, means less than 0. Positive means greater than 0. If it is positive means greater than 0, means what happens? V1 by V2, B sine of beta minus delta will be also greater than 0. Okay. Therefore, either cos or sine. Therefore, what happens? This beta is greater than delta. But under, that is, to make it as a stable condition, you need to choose the admittance angle, or sorry, this is an impedance angle. Beta should be greater than the load angle, so that it will come into a stable condition. Okay. So for a critically stable condition, dp by d delta will be exactly equal to 0. Therefore, if you substitute the same conditions, that is a is equal to 1 at an angle of alpha, that is 0 degrees. If we are neglecting the shunt capacitance and also the resistance, okay, then what happens? B is equal to exactly x, 90 degrees. Therefore, if you are substituting delta is equal to beta, if you substitute delta is equal to beta in this equation, what you will get? V1 V2 by B minus A V2 square by B cos of beta minus alpha. We have also done this one. Okay. This is only for a computation purpose, but this we are including this condition in this one. Anyway, you will get this equation. We have already done this equation. I will show you where we have done. Just I will show you. Show you where we have done this one. See here. If you see clearly here, See, see this equation. You can see this equation. See here, just V1 is replaced with Vs, V2 is replaced with Vr. That's it. The same equation we have done, Vs Vr by B minus A by B Vr square, cos of beta minus alpha. Okay. So that is actually the stability. Okay, because here alpha is equal to 0, so you'll get only cos beta. Okay. Now let us discuss about the methods to improve the stability. Okay, so this is the important one. This I'm unmuting. So whatever, if you have a doubt, you can give a message in the chat box so that I can able to answer your questions, because this is a very, very important concept and so depth concept. I'm unmuting all. So whoever are sitting near to the televisions, or please don't, wherever you have a place so that there will be no noise, please sit in those places. Have all of you gone through the concept? Have you understanding the concept? Not listening. See, no one are listening. After all, you are not there. Manasa, Vaishnavi, Rafiq, Nikhil, Shivasri. Please, all of you raise your hands. All of you raise your hands. So what is the difference between stable and critical stable? What is the difference between stable and critical stable? The difference between stability and critical stability is just like in a control systems, what you're going to use is a marginal stable. Okay, you're going to use in a control systems as a marginal stable, no? That is called as a critical stable in this part. Okay. So who will raise their hands? Then only I will give them attendance. Okay, only 22 out of 33, only 22 raised. Okay, I will give attendance only those 22. Okay, the difference between stability is just less than 90 degrees. We are going to call the system as a stable. Critically stable means it is not as a stable, not as an unstable. But if it is facing any small disturbance, it can move to the unstable condition. Okay, that is the difference between stability and instability, which it will be in exactly on border. Okay? You're going to call it as a critically stable. So only if you have them raised hands. So please ask me doubts. Okay, now, okay, I will discuss about the methods to improve the steady state stability limit also, because we have another 15 minutes time. So what are the methods to improve the steady state stability means? So we already know the power is depending on the sending end voltage, receiving end voltage, and the reactance. So we have 3 chances to improve this stability. Improve the steady state stability means we need to increase this power transfer. So how we can able to increase the power transfer? By increasing Vs, okay, by increasing VR, and also by reducing the reactance. So we have 3 different chances: by increasing the excitation, first of all, by increasing the excitation of the generators or the machines, so that Vs and VR will be getting increased, and also by reducing the reactance. Okay. So that is the same thing you can see here. So the power transfer is directly proportional to the product of the internal EMFs and inversely proportional to the reactance. So steady state stability can be increased by increasing the excitation, that is increasing the excitation of a machine, because usually the generator will have a excitation techniques, right? Because it is a double excited machine, so it will have that technique. Okay, so whenever it is increasing the excitation, therefore the power transfer will also increase. So one method is to increase the excitation of a synchronous machine so that internal EMFs will get increased. So what is another method? Another method is to reduce the transfer reactance. How can we able to reduce the transfer reactance? So we need to reduce the reactance. How can we, what are the different possibilities to reduce the reactance? Okay, the first possibility is parallel lines. If you're using a parallel transmission lines, what happens in the previous condition? If you have this as an X, so now you are using another transmission line. If you're using another transmission line, what happens? This complete factor now, it is not X, now it will be X by 2. Okay, therefore the reactance is reduced if you're using parallel transmission line. If you're reducing the reactance, then what happens? The maximum power transfer will increase. So that's why we are using mostly the parallel transmission line. That is the main reason why we are using this parallel transmission lines. Okay. So what is also another method? If you are using the bundled conductors also, we can reduce the reactance, because bundled conductors will increase the value of capacitance and will decrease the value of inductance, which you already know. If you are using the bundled conductors, will increase the value of capacitance and decrease the value of inductance. Okay, so by using bundled conductors, therefore, if the value of inductance is decreasing, automatically the reactance will also decrease. Okay, so therefore we are achieving the reducing the reactance, therefore the transfer will take place. And again, in reducing the transfer reactance, we also have another condition by adding a series capacitors. If you are adding some series capacitors, so with respect to here, if you have a transmission line, if you are adding some series capacitors, which it is actually minus X value, which you already know the series X capacitors will have a negative reactance. So what happens in the previous case, it is X, but now it is X minus some value. Okay, now it is X1 minus X, because we are adding some series capacitor. Therefore what happens? The total reactance will get reduced. So we have 3 methods so that power transfer will get increased. So we have 3 methods in reducing the transfer reactance. The first one is a parallel transmission lines. Second one is by using the bundle conductors. Third one is by using the series capacitors. Okay, so that we are going to increase the power transfer. That means you are increasing the steady state stability limit. Okay, that indicates you are increasing the steady state stability limit. Okay, so these are the 2 methods: increasing the excitation and reducing the transfer reactance. Again, in this reducing transfer reactance, we also have another 3 methods, that is parallel transmission lines, bundled conductors, and series capacitors. By these 3 methods, we can able to reduce the transfer reactance, and by increasing excitation, we can also increase the power transfer from generator side to the load end side. So this is called as methods to improve the steady state stability limit. So by this, we have completed the steady state stability analysis. So in this one, we have discussed about, just I will go through once. So just we have started about the steady state power limit. This is actually the 3 definitions. Next, we have started about the steady state power limit, how to find out the value of this P. And so then after we have also done, so that we got this equation. Okay. And then after we have found the steady state power limit, synchronous power and synchronous power. And also from the power angle curve, we have derived one condition where X is equal to root 3 times of R. This is the maximum power transfer condition. And to determine the steady state stability, we are going to use some swing equation. And by swing equation, we got that the dp by d delta change in equation, positive, negative, and a 0. With respect to that one, we are going to determining either the system, either the synchronous machine is a stable, unstable, or a critical stable. Then after the methods to improve the steady state stability. Okay. Increasing the excitation and reducing the transfer reactance by using the 3 methods: parallel lines, bundled conductors, and the series capacitors. Okay. So whatever you have doubts, you can please give me a message in the chat box. But still we have a time up to 5 minutes. I'm waiting for your message. We'll discuss that. So I think Aftab is there. Aftab, if you are there, please give me a message. No. Okay. Then who will give me attendance then? Who can able to give me attendance? Only Rajesh, Anjali. Nikhil, can you give me attendance? Nikhil? Oh, it is not getting connected. To whom should I? Please, anyone, please send me attendance. To whom I should ask also, I am not understanding.
Okay, sir. I'll give.
Will you give, Nikhil?
Yes.
Okay, okay. So from tomorrow class, we'll start the transient stability. We have only two stabilities in this syllabus, steady state stability and the transient stability. We have completed steady state stability. Please go through from the starting of the stability class and complete the session of the steady state stability, because whatever you have doubts, you can ask in the tomorrow session. Okay. I think 34 members are there. Okay,
Yes, sir.
34 members are there.
30.
Okay, someone is asking about what happens if total load exceeds the steady state stability limit. It will move to the unstable. Okay, what happens if total load exceeds the steady state stability limit? It will directly move to the unstable, because see, synchronous machine could able to deliver or could able to run only under the stable condition only. So whenever it is crossing this 90 degrees, it will not increase the power, it will start decreasing the power. It will not increase the power, it will start decreasing the power. That means at that time, the synchronous machine is going to be unstable operation. So it is not possible to increase the load beyond. For that reason, we are using the parallel generators, right? To satisfy the load itself, we are using the parallel generators. Okay. So only one synchronous generator or could not able to deliver that so much of load. So every generator will have that capability or capacity. With respect to that capacity itself, it could able to transfer. If that still the load is increasing beyond the limit, means it will move to the unstable operation. Okay, where the synchronous machine will lose its synchronism and it will come out of the excitation system. Sorry, existing network. Okay. Okay, Rahul, and still any doubts? See, transient stability is very, very different compared to steady state stability, because steady state stability is only a small change. Okay, only it is a small disturbance. Okay, either the load or a fault or anything. If it is a small disturbance only, we are going to call it as a steady state stability. If the disturbance is a very large, then we need to discuss about the transient stability. Okay. So that analysis will be different. Okay, those derivations and everything part will be different. So this unit is a very, very important unit, and also I think after is not there. Okay. Okay, anyway, still 1 minute is there. If you have any doubts, please go through once. How can we define the impedance angle? Impedance angle is just like a beta, that is, which it is Z is equal to R plus JX, and impedance angle will be equal to tan inverse X by R. That is, we are going to call it as an impedance angle beta. Okay, which it depends on the transmission line itself. Okay, we are going to call that as an impedance angle. Sometimes in some textbooks they are going to use it as a theta. Here we are going to use it as a beta. That's it. Okay, there is no difference between theta and beta. Okay, in electrical circuits you are going to use it as a theta, but here we are going to use it as a beta. Anyway, the formula is same, which is equal to tan inverse X by R. Okay, that is called as a beta. This angle will also affect, which we have already seen in the derivation. This angle will also affect. Okay, thank you all of you, and Nikhil, please send me the attendance. Okay. Thank you all of you. Have a good day.